You ready to start?
I think so.
All right. Let's get this boot camp on the road. Welcome everyone to the first FlexFlow Bootcamp. So this is all new. And of course, doing this over Zoom is something that, even though many of us have been having meetings over Zoom, I don't think, at least I've been involved in anything quite like this. So it'll be a bit of an experiment, and we'll see. We'll have to learn a little bit as we go. And so hopefully it'll go well. First of all, I want to thank Jihao and Wei for doing all the organization for this, as far as I know. I don't know if anybody else was involved in organizing it. I want to apologize for not mentioning your name, but I know Jihao and Wei put a lot of effort into preparing the boot camp, so thank you very much. And I thought I would just say, a few words about FlexFlow and how we got here. So this started as a research project at Stanford, with Jihao as the principal PhD student. And the idea was to see how if we could use partitioning in multiple dimensions of the data and the computation to improve the performance of deep learning, and particularly deep learning training, but also inference. It turned out to be just as good for inference as for training. And that obviously went well. And once the benefit was demonstrated, we started working with various projects on seeing how much more we could do if we scaled up. And it turned out that at scale, the benefits were even bigger. And so the project rapidly transitioned from a research project to one that's kind of in this intermediate state between something that people can actually use and also continuing to push on the research. So it's still serving a little bit of both roles. But the big thing that's happened in the last year is a lot of engineering to bring it closer to the standard interfaces, to make it easier for people who want to take their existing models and move them over to FlexFlow. So now, just really from starting what was really a custom interface when it was a research project, now there's support for Keras, Onyx, and PyTorch support is there now too, although kind of in, I would say, beta at this point. All right, but moving very quickly towards having support for the standard approaches to building models, and hopefully that will make everything easier to use, and we'll get a chance to see today, how that goes, and you'll see a lot about how to use it. Also, the number of organizations, has grown quite a bit. So after starting at Stanford, now there are major projects also at Facebook and at Los Alamos National Lab, and also involvement from CMU, MIT, Perspecta Labs, and I know Nod Labs is interested, and there's others probably that I don't know about. So welcome, and of course we're always interested in hearing about new applications and having new people involved in the project. And so with that, in the interest of staying on time, I think I will, or at least not being too far behind time. Remarkably, we're already behind schedule, only a few minutes into the bootcamp. So I will stop and turn it back over to Jihao. So take it away.
Yeah, sure. Thanks, Alex, for the kind introduction. Let me share my screen. Okay, so all right, yeah, so let's get started. So first I will give a very brief overview and introduction to FlexFlow, and this is the first time you hear about and to look into any FlexFlow talks. So why we started to work on FlexFlow? So the FlexFlow project is motivated by the challenges in parallelizing deep neural network training. So the left figure shows how we currently parallelize our deep neural network on distributed heterogeneous machines. So we write our model in a computation graph, and we write it in our favorite deep neural network frameworks, can be TensorFlow, PyTorch, MXNet, or many others. And this framework will automatically parallelize our model on distributed heterogeneous machines with different types of devices and memories. But a missing component in this figure is that in addition to provide a computation graph that describes your model, users also have to describe how they would like the model to be parallelized on the given machine. So example parallelism can be data or model parallelism. But this current solution really brings three main challenges. First is that deep learning, especially this tensor algebra computations in deep learning, is very high dimensional and can be parallelized in many possible dimensions. And we have observed that if you use different combination of these data dimensions, you will achieve very different performance on the underlying hardware. And second challenge is that it turns out to be very hard to manually design these strategies. And the current design heavily rely on our heuristics or some ad hoc methods, and require a long time to experiment and evaluate our current design in order to achieve an optimized strategy. And the third challenge comes from the hardware side. So because if we use different device or have different network topology across these devices, they will then the underlying hardware may require a very different strategy in order to achieve the optimal performance. And this really makes today's manual design very hard to port to different types of backends. So FlexFlow is trying to address these challenges by using a different approach, which we try to automatically optimize this DN parallelization. And the key difference between FlexFlow and prior work is that instead of relying on user to tell us how we should parallelize the training, we analyze the underlying machine and device available for training and use this hardware topology configuration to automatically generate some fast and efficient parallelization strategies. And this automation really gives us three main benefits. First is that we have observed by much better performance by automatically discovering more efficient strategies. And we are up to 10 times faster, even compared to the handcrafted and manually designed strategies. And second advantage is much faster deployments. So instead of spending weeks or even months to handcraft how we should parallelize a model on a given parallel machine, in FlexFlow, we only use a few minutes of automated search to discover this performance strategy. And also, we require no manual efforts for portability. So if you would like to run train for a new model, or you would like to run your current model on a new hardware platform, you can directly run FlexFlow search, and it will automatically find an optimized strategy. Okay, so how FlexFlow interact with existing systems? So currently, you can think of FlexFlow as a distributed DN execution engine, and we support deep neural network models implemented in existing frameworks, TensorFlow, PyTorch, Onyx. And we have also implemented domain-specific systems on top of FlexFlow to optimize new deep learning applications, such as graph neural networks. Okay, and so for the next of this bootcamp, the next talk, Vinay will talk about installing FlexFlow and getting started, the basic usage of FlexFlow. And after that, Wei and Mandeep will talk about our recent support, front-end support for existing frameworks. So how we can transparently run existing DN models in Keras, PyTorch, or Onyx on FlexFlow. And finally, Nirmal and I will talk about automatically optimizing and profiling DN parallelizations in FlexFlow. Okay, so as I briefly mentioned earlier, the key idea of FlexFlow is to searching for high performance strategies, and this involves two key components. First is that we try to define a very comprehensive search space of possible parallelization strategies, and try to identify possible and potential ways to parallel DN training. And second, in FlexFlow, we use a cost model to evaluate different candidates in the search space. And so basically for different parallelization strategies, the cost model will tell us which ones are more promising. And we also involve a search algorithm to allow us to quickly find highly optimized solutions. And by combining these two key components, we are able to discover highly optimized strategies. So what is the search space used in FlexFlow? We call it the SOAP search space, which considers 4 different types of dimensions to parallel training. So they are the sample, operator, attribute, and parameter dimension. So let me tell you the meaning of these 4 dimensions. First, the sample dimension is considering partitioning training samples, and this is also called data parallelism in existing frameworks. And the bottom figure shows parallelizing a convolution using the sample dimension. Because the convolution can be parallelized in 3 dimensions, so we use a cube to describe the computation. And by using the sample dimension, we end up assigning different training samples to different GPU devices. And the second dimension is called the operator dimension, which considers partitioning ML operators across devices. And this is also called model parallel dimension in existing frameworks. And the idea is that we can assign the entire computation of different operators onto different GPU devices and run these operators in parallel, as long as there's no dependencies between these operators. And the next 2 dimensions are the new dimensions we created in FlexFlow that hasn't been well supported in previous frameworks. And there is also why when the magic happens. So the third dimension is called the attribute dimension, which considers we can partitioning model attributes within a training sample. So you can simply think of attributes as pixels. So if you have a high resolution image, you can partition the image into multiple sub-images and train different sub-image on different devices. And so later in this talk, I will show that this attribute dimension is very critical for parallelizing graph neural network, which is a new emerging category of deep neural network models. Okay, so the last one is called the parameter dimension, which considers partitioning the parameters within an operator across devices. And the benefit of using this dimension is that because the gradients for each parameter is only computed on a single device, so we can fully eliminate the communication overhead for synchronizing model parameters. Okay, so in addition to these individual SOAP dimensions, we also consider this hybrid parallelism in SOAP by combining multiple SOAP dimensions. And the right figure shows using 2 or 3 SOAP dimensions for one deconvolution. And in our design, it is guaranteed that different strategy will perform the same computation. And therefore, we can get the same model accuracy by using different strategies. And the key advantage of this design is that when we are trying to decide how we should parallelize the training of a model on a given machine, we don't have to worry about potential model accuracy loss and can focus on improving the runtime performance. So how a strategy in SOAP looks like. To give you some visualization examples, the top figure shows how data parallelism looks like for Google's Inception modular. So each box here indicates the computation for one operator. And we have 2 dimensions here. We have a horizontal parameter dimension and a vertical sample dimension for each operator. And a different color means we assign the corresponding computation to different GPU devices. And by using data parallelism, we always end up assigning different training sample to different GPU devices. And the bottom figure shows how a possible parallelization strategy in SOAP looks like. And it is 1.2 times faster than the previous data parallelism. And in this strategy, we can use data parallelism for some layers. We can use model parallelism for some other layers. And we can also use hybrid parallelism for intermediate layers, and also support different degree of parallelism for different operators. So you don't have to parallelize all operators in the same degree. And SOAP really defines a comprehensive search space of possible ways to parallel ML training. But it is also challenging to discover fast strategies in SOAP. The first challenge is that SOAP contains billions or even more possible strategies. So we cannot enumerate all single strategies in SOAP. And second is that evaluating a strategy is very slow on hardware. For example, evaluating the performance of one strategy may take a few minutes. But in order to find optimized solution, we may need to consider thousands or even up to millions of candidates. And to address this challenge, FlexFlow used MCMC Markov chain Monte Carlo search algorithm to explore the search space. And we also built a very accurate execution simulator that can predict and evaluate the performance of different candidates in the search space. Okay, and this shows an overview of FlexFlow. And as we have seen before, FlexFlow can take computation models implemented in existing frameworks. And we also take as input a hardware topology graph that describes the devices that will be used for training and also the interconnection between these devices. And FlexFlow use the Markov chain Monte Carlo search algorithm to generate candidate strategies. And these candidates are sent to the simulator for simulating the performance of different candidates. And the simulated performance will be sent back to the MCMC search algorithm. And when the search procedure is completed, the best found strategy will be used for parallelizing training. And the design of our simulator is based on two key observations of machine learning, especially deep neural network computations. And the first observation is that the performance of most ML operators is highly predictable. And this is because most ML operators are based on dense linear algebra, and their computation time on current accelerators is very reliable and predictable. And the second observation is that although some ML operators may have hundreds or up to thousands of operators, but it turns out that most operators in an ML model are the same, and each model only have a very small number of distinct operators. And by using these two observations, we can directly measure each distinct operator and communication bandwidth once, and can use these measurements to simulate different strategies. And this achieves very fast simulation and also achieves a high accuracy. And we will cover more about this in a later talk. Okay, so by using FlexFlow and automatically optimizing parallelization, we found that we are faster and even more scalable than the strategies that are manually that are carefully crafted even by domain experts. And so at Facebook, we have been using FlexFlow to train DLRM, which is a deep learning recommendation model. And so the DLRM model has a mixture of compute and communication intensive workload. And so that makes this model very hard to parallelize in data or model parallelism. So from this figure, the x-axis shows using different number of GPU for DLRM training, and the y-axis shows the overall throughput achieved by using that number of GPUs. And as you can see that we cannot achieve higher throughput compared to single GPU performance. But by using FlexFlow, we are able to discover much more efficient strategies and achieve up to 10 times speed up. And so in this bootcamp, this DLRM model will also be used as an example for demonstrating the performance auto-tuning functionality in FlexFlow. So we will revisit this model in a later talk. Okay, and FlexFlow is also used at Los Alamos National Lab to train ECP-CANDLE, which is a deep learning model for precision medicine. We are trying to predict the response of a drug on some human body cells. And by using, so first we try to run this parallelization model using data parallelism in TensorFlow, but we found that it cannot scale beyond the capacity of a single machine. So when we move to multiple nodes, the throughput starts to drop. And but on the other hand, FlexFlow can scales to up to 768 GPUs and can reduce the overall training time by 15 times. Okay, and so we have using FlexFlow as a foundation. We have also implemented some other domain-specific systems for optimizing new categories of deep learning applications. So graph neural network is one example. So we have built a system we call ROC on top of FlexFlow that can improve the accuracy, scalability, and also performance of graph neural network. And graph neural network performs different from conventional deep neural networks. Graph neural networks perform neural network computation on graph structure data. so such as social network, knowledge graph. And graph neural network also shows very different challenges compared to deep neural networks. So unlike deep neural network that has small and regular intermediate data and achieves very good efficiency, so graph neural network actually has very large and irregular intermediate data. And this results in both efficiency and scalability challenges if you would like to run GNN computation on GPU devices. And existing deep learning frameworks also cannot support very large graph neural network training. This is because if we run GNN training using data parallelism on existing frameworks, we end up process each training sample, which will be graph here, on a single device. And so then as a result, data parallelism really limits the scalability of GNN computation because we cannot support large graphs beyond the capacity of a single GPU device. And so the key insight in ROC is to explore the attribute parallelism for a graph neural network. And remember that we have when we talk about the SOAP search space, this attribute parallelism means attribute means pixel for convolutional neural network. So we can partition the image into sub-images. And similarly, in graph neural network, attributes are vertices. And by using attribute parallelism for a graph neural network, we can end up train different subgraph on different GPU devices. And we found that attribute parallelism is very critical for graph neural networks. And the opportunities is that most real-world graphs have billions or even more attributes. And compared to data parallelism that train models across different samples, this attribute parallelism discovers additional parallelization opportunities within a single large sample. And so one problem we have to address is that if we use the attribute parallelism, we need to maintain consistency between different GPUs because they will share some vertices along the boundary. But FlexFlow already have the automated support for synchronizing attributes shared among GPU devices. So to address the other challenges of graph neural networks, so the challenges are that real-world graphs are very large, which means the intermediate results may exceed the GPU memory capacity. And large real-world graphs are also very irregular, which will result in power law degree distribution and cause significant load imbalance. And to address these two challenges, in ROC, we use dynamic programming to, because FlexFlow already supports training using heterogeneous memories. So in ROC, we add a dynamic programming algorithm in FlexFlow to manage heterogeneous memories in FlexFlow and also minimize data movements. And we also use a linear regression cost model for graph partitioning. And it will compute balanced graph partitioning and result in so solve the imbalance problem. And so using FlexFlow as a backend, ROC enables high performance and very large scale GNN training and inference. And we show better efficiency by outperforming existing frameworks by 4 times, and also shows much better scalability. So we can enable training of up to 64 times larger GNN architectures compared to the largest GNN that can be supported in existing frameworks. And so by using these significantly deeper and larger models, we exercise ROC by using these large models on existing data sets. So we train existing data sets, but use much larger models than prior work. And we found we can achieve better accuracy. And more specifically, we can improve state-of-the-art model accuracy on the Reddit, which is a commonly used GNN data sets from 65.4 to 68.6.9. And so we think ROC shows an example where FlexFlow and automated parallelization in FlexFlow can help us optimize new deep learning applications. Okay, so for the last part of my talk, I will briefly describe the new features and also the new optimizations that will be available in the upcoming FlexFlow December release. So the first feature that will be available in the next release is our automated support for large models and training samples. So in the new released in the new stable version of FlexFlow, we can directly support large DLRM models that do not fit on a single device or even on a single compute node. And some examples include some large language models such as GPT-2 or GPT-3, and also some recommendation models such as DLRM. And we also added support for large training samples that do not fit on a single device or compute node by using the attribute dimension. And we can support some high resolution images and also large social network graphs. And the next feature that will be available in the next release is our system optimizations for heterogeneous devices. And these optimizations lead to much better runtime performance and also better scalability. So we can, by automatically searching for strategies that uses these heterogeneous devices, we can optimistically accelerate DLRM training by parallelizing the computation on different types of devices. And this also allows us to support models that are beyond the aggregated GPU memory capacity. Okay, so in addition, we will also add some optimizations for parameter synchronization methods. And in the next release, FlexFlow will support two methods to synchronize parameters. So one is a distributed parameter server, in which case each GPU and compute device will be the parameter server for a subset of parameters in your model. And in addition, we also support for each operator, we also support an alternative or reduce method that use existing NVIDIA NICO library. And so on the search side, we will also add support for that can automatically optimize parallelization synchronization by using the more efficient methods during the MCMC search. And there are also many exciting research projects on top of FlexFlow. And just to name a few, so one ongoing research project called TopoOpt is trying to jointly optimize network topology and with parallelization for distributed DLRM training. And the key insight we have here is that existing DLRM frameworks, including FlexFlow, are optimized for traffic oblivious network topology. We assume that different node pairs have the exact same bandwidth, but we found that this traffic oblivious assumption is really suboptimal for deep neural network training. And so in this project, we are trying to explore opportunities to jointly optimize parallelization in FlexFlow with network topology in TopoOpt by using reconfigurable network architecture. And recently we have achieved very promising preliminary results. So our simulation on 16 nodes for DLRM shows that we can achieve 1.5 to 3 times speed up compared to using the traffic oblivious network assumption. Okay, so to conclude, FlexFlow enables automated discovery of fast parallelization. And overall, currently FlexFlow is an active research project across many institutions. And our goal here is to provide extreme flexibility and also automated optimizations for large-scale distributed deep neural network training. And we welcome any types of contributions to our community. Okay, so with that, I want to conclude my part and just in time. So any questions before we move to the next one?